So today is the second lecture of Harvey Friedman, and he will speak about invariant maximality and choice. Please.
Thank you, Andreas. So this is the second lecture and on invariance in piecewise linear and semi-algebraic sets. And I have some good news. I have reworked this chapter 2 and upgraded it significantly, and with some simplified arguments and some additional material. And the main success is that I've consolidated all of the notions of invariance beyond the simple shift invariance into a single notion, invariant shift invariance, for the entire book. So this notion, invariant shift invariance, interval shift invariance, is used not only for this introductory material in the first two lectures, but also it's used for the independence results, for the independence results statements. And the title of chapter 2 has been simplified to shift and interval shift invariance from what it used to be. All right. And in fact, the old lower intervals invariance, the old lower shift invariance was actually a special case of the interval shift invariance, of the new interval shift invariance. Actually, that yeah. Okay, so let me continue here. Now let's see. Yeah. So I'm nearly done with the rewrite of chapter 2, which will be put on the downloadable manuscripts before I give lecture 3 on the 24th, which is 1 week from now. And lecture 3 presents the implicitly pi01 sentences that are independent of ZFC. So the new table of contents for the book is slightly changed. Book title is called Invariant Maximality and Choice, with an introduction. Chapter 2, which we're finishing up today, Shift and Interval Shift Invariance. Chapter 3, Invariant Maximality and Choice Derivations, which is the forward direction. Chapter 4 is the reversals, and chapter 5 is the finite forms, the explicitly finite forms. And the third lecture will be presenting these statements. They all come, the statements that are independent of ZFC all come from statements that are not independent of ZFC. Every widget has a gadget. As I mentioned last time, there's a whole bunch of statements. Every widget has a gadget which are proved, and every widget has a maximal gadget. Every widget has a maximal gadget, which are proved in RCA naught with no issues involved. Then the action starts when you put the invariance on there. So every invariant widget has an invariant prime maximal gadget. These are the incompleteness. These are the statements that are independent of ZFC. This will all be clear in the third lecture. All right. That's the itinerary. All right, now for the main events here. Shift invariance from last time, just reviewing, you have a subset of R to the K, and S is X1, 2 through ... shift invariant if and only if these are real numbers. And for any K tuple, membership in S remains equivalent when we replace each xi by xi plus 1. So that's like a shift to the right. Now, we do allow there to be the finite case, x1 through xn. We now come to the key definition that drives the entire book. And we always use J for non-degenerate intervals in the reals. All right, so here it is. So I have a subset of R to the K. S is J, comma, x1, x2, dot, 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 shift invariant. If and only if the infimum of J is less than the supremum of J, which is just saying that it's non-degenerate, which I already said by convention, right, anyways. But here it is, inf of J less than sup of J less than or equal to x1 less than x2 less than dot, dot, dot in the reals. And for every y in J union the x's to the kth power, membership of y in S remains equivalent when we replace each xi by xi plus 1 in y. And we'd allow x1 through xn, we allow the finite case, x1 through xn. So that's the definition that drives the whole book. Just this one here. All right. In chapter 2, we analyze, in the chapter we're talking about, the whole business is analyzing the following statement. Every arbitrary or piecewise linear or semi-algebraic S contained in R to the K is J x1, x2, dot, 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 shift invariant for some J x1, x2, dot, dot, dot. That's what chapter 2 is about, that of which this is the second and final lecture. That every nice or arbitrary or nice set is J x1 through x2 dot, 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 shift invariant for some J x1, x2 dot, dot, dot. And that's the interval shift invariance I just defined. It's interval shift invariance because there's a capital J there. But we also make some important modifications that strengthen a statement I with certain uniformities. So we consider 1, 2, 3, 4, 5, 6, 7, 8 modifications. The first two, these particular numbers, the number 0 here is an arbitrary constant that's just convenient, and it doesn't make any difference because of symmetry. So with the first two modifications, we're actually fixing the endpoints. And that's actually very strong to get that. Minus infinity and other numbers are different. So minus infinity is a special case. We fixed the first, we fixed the left coordinate or the first endpoint, sorry. We fixed the first endpoint to be minus infinity or 0, and we let the other endpoint be quantified existentially. And then we reverse that P, 0. Then we also modify by demanding that the right endpoint of the interval be the same as the first indiscernible. Think of the x's as indiscernibles here. X's are the things that are being shifted. So this is very important to consider the case where the right endpoint of the interval is the same as the first indiscernible. And of course, all of you who know set theory know how the significance of that. And we use the convention of using left open, right closed, as in the definition. In the definition, we use a left open, right closed, because there's no loss of generality here, because we can wiggle the endpoints. All right, now we have three main sections in this talk. In the bulk of the talk: arbitrary, piecewise linear, and semi-algebraic. Arbitrary, piecewise linear, and semi-algebraic. And in one dimension, things are, of course, trivial, because interval shift invariance and regular shift invariance are the same in dimension one. So you can ignore the interval. And of course, you get a triviality in one dimension. Now, in two dimensions, in the arbitrary case, everything collapses, everything is negative, nothing works. So interval shift invariance doesn't work for if you want arbitrary inputs, arbitrary hypothesis. And this is for the following reason, which I did mention last time, but it's worth mentioning again. There's a low-level Borel function, f, from the reals into the reals, which is surjective on every interval. Remember, my intervals are, by convention, always non-degenerate. And I decided not to go through the proof of this. It's so different than other things. But it's, it's one of these elementary kind of descriptive set theory constructions where you make a bad function that diagonalizes over what you want. You have to make sure that this is a countable diagonalization, however. Otherwise, it doesn't make any sense, right? So, but what I have not explored is what can you say as a descriptive set theorist about the complexity of such an F. Obviously, such an F can't possibly be continuous or even close to continuous, right? Okay, now using that function from theorem 1.2, we can immediately get this big negative result that kills dimension higher than one. Namely, there's a low-level function, Borel set in two dimensions, which is not J x1, x2 shift invariant for any J x1 and x2. You just need, you can't even get two indiscernibles, and the proof is obvious. And this kind of proof, occurs again in various forms throughout. Let S be the graph of F, where F is this function I mentioned. And suppose you had, suppose you were a J x1, x2 shift invariant. You let Y be in J, where F of Y is x1. In other words, you take the inverse of x1 on the interval J, which exists by the construction of F, and then x1 is in S, and yx2 is not in S, right? So the equivalence fails. All right, so now we come to something more substantive, piecewise linear. Now, this will be somewhat non-trivial, but not as interesting, certainly, as the final case, which is the semi-algebraic case. So we're now looking at this statement: every piecewise linear set S is J x1, x2 ... shift invariant for some J x1, x2 ... Now, with no modifications, this is true. And it's even true in a very strong sense that I can require J to be -1, 0. In other words, I can fix in advance the interval. However, if I try to fix it in advance by being more ambitious and making a bigger interval, namely this one, -∞, 0, it's false, even in dimension 2, for x1, x2, it's quite easy to see this. Minus infinity 0 is too big linearly, because if you take negatives, you get the whole rest except 0. All right. Now, if you require j equals minus infinity p, where p is existentially quantified, then it's true in dimension 2, but false in dimension 3. And the falsity comes from, well, separate this out. It's just flat out true in dimension 2, but it's false in dimension 3 for x1, x2. And you can actually fix the left-hand point to be 0 for j equals 0p. It's true. Since it's already true for minus 1, 0. Okay. Now we come to when the right endpoint is the same as the first indiscernible. So if we require that j be minus infinity x1 or 0 x1, then it's false in dimension 2 for x1 and x2. Because you can go dip down from x1. You can dip down, you know how to dip down from x1, and when you come back to x, you can't come back to x. When you come back to x1, you can't come back, you can't get up to x2, right? So therefore it's false. I mean, these are simple things. Now, if I require that j be p of x1, where p is existentially quantified, then it's true because I can set p equals 0. Okay, so that's pretty comprehensive. So the main positive result here is the principal positive result is that you can do this for minus 1, 0. You know, if you just give me two numbers. And that has to do with fast growth rate. You just make sure the x's are high up and grow fast. And we talked about this last time. You just need geometric progressions because things are linear. Okay, semi-algebraic is, of course, more involved. Now, I didn't mention last time, but and I will in the manuscript mention that the only kind of things I'm using for this are O minimality. So all of this holds in an O minimal system, of which the primary one is, of course, the real closed field with the reals. The reals, yeah, the ordered field of all reals. And I defined piecewise linear and semi-algebraic last lecture. All right, every semi-algebraic set is j x1 through x2 dot 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 shift invariant for some j x1 x2 dot dot dot. This is actually this is somewhat delicate. This requires some work, far more than anything with the piecewise linear. This is true in dimension 3. Just the statement as is, and it's false in dimension 4 for just two indiscernibles. So it's true in dimension 3, false in dimension 4 for two indiscernibles. If I insist that I present you with minus 1, 0, then it's true in dimension 2, but false in dimension 3 for x1, x2. And with piecewise linear, I could do everything, you see. Now, for minus infinity 0, I had trouble with piecewise linear. I have the same trouble with semi-algebraic, but no more trouble. So it's false in dimension 2 for x1, x2. Yeah. All right. Now, when p is existentially quantified, I get truth in dimension 2, and I get falsity in dimension 3 for x1, x2. So there's a lot of stuff here that's okay in 2 dimensions, but not in 3. And then if I fix a number or minus infinity and I make the right endpoint x1, then I get into trouble with even in dimension 2. But that's true even in piecewise linear. Okay, so that is a summary of the situation. I will actually go into some detail about a few of these, a little more detail about a couple of these. But now let's talk about this in general linear orderings. So let W be a linear ordering. So now we have the statement, every subset of... now, when I do general linear orderings here, I don't have any structure. I'm not assuming any structure. And so I'm talking about the arbitrary case. And if you remember, the arbitrary case collapsed pretty quickly. But this is different because I'm looking to make up a linear order. I'm not giving you the reals. This is no longer in the reals. This is a somewhat different subject where I'm allowing us to make up the linear ordering. So we have every subset of WK is J x1 through x2 dot 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 shift invariant for some J x1 x2 dot dot dot. If this holds for some infinite J in W, then the cardinality of W is at least the first uncountable strong limit cardinal. So this packs some power. If this holds for some J equals 0 x1, and actually I didn't quite mean this. I mixed this with the ordinal case. I have here a mistake. For some J P x1. Sorry, I'm going to write this. P existentially quantified. Then for all K, there is a KSRP cardinal below cardinality of W. So if you have this, then you are into serious large cardinals. W has to be very large. Okay. So now you realize that there's a connection between these first 2 lectures that live in these lectures. First 2 lectures live in RCA naught and the large cardinal. If you shift the linear orderings and ask for certain kind of thing, you get into set theory. All right. Now there's a relevant paper for these kind of cardinals, which is, by the way, the book is surrounding the large cardinal theory in the book is all at this level. There's a paper of mine, Subtle Cardinals and Linear Orderings, in 2000. All right. Looking at the general case in the ordinals. So now I'm back to telling you what the linear ordering is, or at least somewhat telling you. It's something lambda. It's some lambda where lambda is a limit ordinal. We have the statement every subset of lambda to the k is J x1 x2 dot 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 shift invariant for some J x1 x2 dot dot dot. For J, any fixed interval in lambda, this statement holds if and only if lambda is a strong limit cardinal. That's not quite. Is that actually what I mean? Yeah, I think that's right. I gotta check that that's exactly right, but I think that's right. Yeah, and if for J equals alpha x1, alpha quantified, this statement holds if and only if lambda is KSRP for all K. So this is a large cardinal axiom, basically. These things that are in that RCA naught that I was talking about, when you shift the context in this way, is large cardinals. So in the ordinals, we have analogs. Now, here's something intriguing I just thought about when preparing this lecture. In the ordinals, we have analogs of piecewise linear and algebraic using ordinal addition and ordinal multiplication. Well, maybe also ordinal subtraction in some sense. We also have natural addition and natural multiplication, or Hessenberg, so-called thing, and other basic operations. We can use these operations to form natural classes of subsets of lambda to the k, right? And we can revisit interval shift invariance here. So this lecture is about piecewise linear and piecewise algebraic and algebraic with some work on general. We can do this on the ordinals. And we have piecewise linear and algebraic subsets of the ordinals, which is probably not quite the right names for them. Because there are issues about negative coefficients, exactly what you should mean. You might want to call them, I don't know, positive. Anyways, there are many possible natural classes of functions that are good here, that are somewhat analogous to the good functions that I was talking, natural sets and functions, analogous to the natural sets and functions in core math that I've talked about in these two lectures. So revisit everything for those. That probably won't involve that may not involve large cardinals because the functions are so basic, if you follow this kind of thing. All right, now I want to talk about this result in 2 dimensions. I did remark that this is actually true in 3 dimensions, but that'll come later at the end of the talk, near the end of the talk. All right, so every semi-algebraic set in 2 dimensions is j x1 x2 ... shift invariant for some j x1 x2 ... This is true as is, but it's also true for p x1, where p is existentially quantified. And these follow immediately from, I should call it Ramsey's theorem for pairs of reals. Yeah, that's probably what I should give a name to this. This is Ramsey's theorem for pairs of reals. But it's only the semi-algebraic case, of course. So let S be semi-algebraic in 2 dimensions. There's an interval J such that for all order equivalent X and Y in J squared, X is an S if and only if Y is an S. This is very false in dimension 3. In fact, in dimension 3, you can't even get a set J of order type minus omega plus omega. I mean, obviously, you can get a set of order type omega or minus omega by infinite Ramsey's theorem. But you can't even do this for at all for order type minus omega plus omega. And in fact, you can't do this for a set S that's piecewise linear. In fact. All right. But you can do this in 2 dimensions when S is semi-algebraic. Actually, I'm not 100% sure that that's new. I don't think it's well known, but it's possible. Anyways, theorem 3.1 can be used to give a proof of the following. Let F go from R squared into R be semi-algebraic and let D be a real positive real number, there exists J such that F, the forward image of F on J squared, omits an interval of length D. You can't get automatically an interval of infinite length there, but you can, it omits intervals of arbitrarily large length, finite length. In fact, it wasn't even known, or at least stated in the literature, that you can get a J such that Fj squared is not everything. A non-surjective theorem. This appears to be an overlooked result in semi-algebraic geometry. It's false in 3 dimensions because of 1 over x minus y plus 1 over x minus z. All right, now, to get theorem 3.2 from theorem 3.1, let f from r squared into r be semi-algebraic and let d be greater than 0. And look at 4 intervals, minus infinity d, d 2d, 2d, 3d, and 3d infinity. And by theorem 3.1, we can find j such that f omits one of these 4 intervals over j squared by the Ramsey theorem. A Ramsey theorem for pairs, pairs of reals, right? Since there are only 3 order types of pairs, there are only 3 order types of pairs. So by the homogeneity, you've got to be missing one of these intervals. All right. So we use this, we can to sketch a proof of this. Let S be semi-algebraic as I advertised, then I can find a J such that for all order equivalent X, Y in J squared, X is an S if and only if Y is an S. The idea is to define a strictly dominating semi-algebraic G such that given if I fix the first coordinate X, the first endpoint X, and I make the other endpoints, the other endpoint is bigger, of course, that at least as far as you go out, G of X, we have the indiscernibility. We have the homogeneity with the first coordinate fixed as X. We can always do that by elementary semi-algebraic theory. We can always do that. It's like a one-dimensional form of what we're trying to do. And now we have a function from the reals to the open interval 0 infinity. I forgot to say that G is actually the difference between G of X and X. Yeah. So G is defined to be the difference. How far out you have to go from X in order to, how far can you go out? How far out am I going from X in order to get the one-dimensional homogeneity? Yeah. So now we have a function that's positive, strictly positive on the reals, that's semi-algebraic. It has a lower bound P. It has a positive lower bound P. And then if you look at this carefully, you will see that you can just use that J on which the function is greater than P. You can just use that J for what we want. In other words, we get homogeneity with say this fixed, these fixed a certain amount, but then we're really covering a lot of the intervals, and so we get it for all pairs. All right. Now, there's a couple of straightforward strengthenings of this that can be proved the same way. So if I have n subsets of R squared that are semi-algebraic, then for every J, there exists a refinement J prime contained in J, such that for every I less than or equal to N, we have the homogeneity for each SI inside J. Sorry. Excuse me. Yeah. You have the homogeneity in J prime. And then we can get the multiple version, a strong multiple version of the function theorem. That if I have n functions from R squared and R that are semi-algebraic, and I have a quantity d bigger than 0, then for every j I can find a refinement j prime contained in j and an interval j star of length d, such that each fi j prime squared omits j star. Just the obvious generalization, prove the same way. But I didn't want to start with that because it clutters up the idea in a lecture. All right. Now, theorem 3.4 can be used to prove this theorem, which is stronger than what we just, with the other one. Every semi-algebraic S contained in R to the third is J x1, x2, ... shift invariant for some J x1, x2, ... And as I said, this is very false in dimension 4. And you can get this by using theorem 3.4 to get two intervals, one strictly below the other, where membership of U in an element of J squared cross J prime depends only on the order type of U1, U2, and the actual number U3. You see, this is obviously stronger than before. Just the pure Ramsey theorem was just depends on the order type of U1, U2, and there's no U3 at all. But you can actually do this from this function theorem that I mentioned. And then by shrinking and reapplying, and the shrinking goes on because you go from J to J prime down to J double prime and all that stuff. By shrinking and shifting the two coordinates, we can additionally require membership of U in J cross J prime squared depends only on the order type of U2, U3, and the actual number U1. And now we're getting close to actually checking J x1, x2, ... shift invariance. We're getting very close. There's only one thing missing, and that is that the x1, x2, ... have to themselves be fine with the triples in there. The triples in there have to be all handled properly. They have to shift properly, the triples. But that's just pruning any x1, x2, ... from J prime by the usual infinite Ramsey theorem for three tuples, arriving at the desired J x1, x2, ... And of course, you don't have to use full infinite Ramsey theorem for this. You can use RCA naught because you're in a semi-algebraic situation with order type omega. And so you can just do stuff. You can estimate how far out you have to go and stuff. So I can stay in RCA naught. All right, so let's welcome. Okay, so this means that I have proved probably the highlight of the highlight positive result in this semi-algebraic stuff. Namely, you can get the interval shift invariance you can get in 3 dimensions. That doesn't mean you can get any of the modification. I mentioned these other modifications, they're all false. 3 dimensions. all these strengthenings where you look for more uniformity and stuff like that. You can't do that. And of course, as I said, you can't get this at all in 4 dimensions. Now let's come back to a claim that I made. I claim the following is false. Let E be piecewise linear in 3 dimensions. There is an S of order type minus omega plus omega, such that all order equivalent X and Y and J to the third, it's homogeneous. Homogeneous. For a set of, in other words, there's a homogeneous set of type O minus omega plus omega. Now, obviously, there's a homogeneous set of type omega or minus omega by infinite Ramsey's theorem. And again, you can use RC and naught also to do that. So the counterexample is you look at the set of triples such that X is less than Y is less than Z, and Y minus X is less than Z minus Y. In other words, there's a bias. It's like looking at 1 to a million, 1 to a million, 1 comma 2 comma a million, right? There's a bias. Together with just the triples that go the other direction, X greater than Y greater than 0, would just have X minus Y less than 1, a simple thing. Then I claim I don't have a homogeneous set of type. Let's say I do have a homogeneous set of type minus omega plus omega. It will get a contradiction. So in the first case, this is a pretty simple thing. In the first case, I want to look at is when the sup and the inf are infinity. When the sup and the inf are infinity, you can do anything you want with the first part of E. The first term of E. It's a union of 2 sets. You can do anything you want, right? You can make the first term 2 terms close and the other one far away, or make the second and third terms close and the first term far away, clearly. Because the sup and the inf are both in, the sup is infinity and the inf is minus infinity. You can do this. All right, now what if the sups are finite and the inf is finite? You can also do this if you think about it, because you're getting close, you can get very close to the inf with the little ones and very close to the sup with the big ones, and then you can fool around with making the first 2 close and the last one far and so forth. Okay. Well, that's too far apart. Yeah, far apart. I mean, yeah. And then the other cases are when the sup is infinity and the inf is finite. And in these cases, it's easy to see that you can make the first 2 terms less than 1, or make the first 2 terms differ by 1, or closer than 1, or make the first 2 terms farther than 1 without any problem, because one is going to infinity, the other is limited. So that is a contradiction. And guess what? I think I'm finished. Andreas, where are you? Anyways, he didn't think I would finish this quickly, but
well, that's fine. So
maybe I'll say a few more words, though. Wait a minute. Did you close the recording yet? I hope not.
no, it's still all recorded.
All right. So what we're going to do next time, you understand this first 2 lectures, I take now in retrospect, I have interval shift invariance driving a lot of large cardinal theory that's already existing that I wrote about. You can talk about it as interval shift invariance. even drives it in linear orderings. I decided to look into it, how it drives it in piecewise linear and semi-algebraic sets in the reals. And you get a whole bunch of pretty core mathematics with some new insights and problems. And then we're going to talk next time about how I put it into every widget has a gadget. We're going to look for every order invariant widget has a shift invariant gadget. And we're going to get the equivalence of that with con SRP. That's what this is about. So we have this one idea, this one parameterized form of shift invariance, which in different contexts give you core math, give you large cardinal combinatorics directly in set theory, and give you large cardinal combinatorics consistency in simple countable combinatorics. That's what we're going to start. We're going to start all fresh all over again next time. And I won't be using any of these first two lectures. Now, Andreas, you have the floor.
Yeah, thank you very much. I will now stop the recording.